apologies to you, Dan. So, professional software development from Microsoft. I've been working in local search team. So, please welcome Dan.
Thank you. So I think the purpose of today's talk is mainly that we're going to be doing a sequence or a series of different talks in C++, and we want to try to get a sense of what the level of understanding of everybody is and what everybody's hoping to get out of it. So we're going to go over some things at kind of high level today, just kind of thinking about these are the sorts of problems you might run into when you're programming, what is it that you're comfortable with, what is it that you want to learn. So basically answering the question of why are we actually here today. So these are some of the things that I was thinking about before class that after sort of discussing with Igor, kinds of things people were wondering about. Tried to summarize them a little bit. Hopefully your cases fit into some of these. Certainly if you have other reasons for being here, you should let us know and then we can try to adopt accordingly. I think big reason people would have, my code has too many bugs, so you want to try to figure out, you've written all these programs, how do I get rid of all these bugs? Maybe you're not quite sure what are methods, what are classes, what are functions, trying to understand how these can actually be useful. You feel like they're just kind of overwhelming amount of syntax, not really quite clear the benefit. Pointers are scary. I think that's a very common claim that people make out of C++, or if they're using stuff in C as well. Standard library is not standard. This is a complaint also in C++. Very difficult to use the standard library. There's a lot of stuff that is given to you in the library that you can make use out of in your program. And if you use it correctly, you save yourself a lot of time in terms of the amount of programming and code you have to write. But on the other hand, there's also a lot of things that are kind of weird about that. So hopefully we can try to clear up a couple of these different things. My programs are too slow. So you write this program, logically everything is correct about it, but then when you go to run it on your big data set, it just doesn't work. It takes 8 hours to run, or maybe it doesn't even finish at all. So what can one do to try to improve the runtime of your program so that it doesn't take quite as long? I heard databases are important. So something you maybe think this is a useful thing to know, you're trying to store lots of information. What's the purpose of them? So we can go into a little bit of talk about that. Inheritance is confusing. I thought I was getting paid money out of it. So this is somebody who maybe just reads the term inheritance and thinks that they're inheriting a big fortune of something and then realizes that in C++ inheritance doesn't actually mean quite what they think it is. So we can talk a bit about what the benefits out of inheritance are. I think a lot of times you end up seeing all these different structures in code and you don't really get what the motive for why you would want to use that. So I think one of the main purposes of this in all of these should be not just so much, here's what the syntax is, this is what will happen if you do this, but really why would you even want to do this kind of thing in the first place and what benefit can you get out of that? So we're going to try to go through some of these today, just not so much how you would do it, but what the reason for why you would want to learn it is, because I don't think there's any point of spending hours trying to understand some syntax and then you learn it and you don't actually get any benefit out of it. So try to motivate some of these. A couple other things, I have no idea why I'm here, but programming is cool, so it might just be you want to learn a bit more about programming. I noticed also when I was making the slide that every single one of these I added exclamation points to because I was very excited, so maybe you just actually love exclamation points as your other reason. So, okay, so we're going to talk a little bit about each of these. So just kind of going through them, we'll talk a bit about computer bugs. I want to talk a bit about why they actually happen, what one can do to try to minimize them. It's kind of not any easy answer, unfortunately. There's no magic thing that says, okay, get rid of all the computer bugs. Generally, bugs have happened ever since computers began. So this is not some new problem in computer science that all of a sudden we just started getting computer bugs. We've always had them ever since we started programming computers. I have a couple of relatively famous examples of computer bugs. Supposedly this is the first ever computer bug where somebody was running their program through something and they actually discovered a moth, an actual bug in their program. And so this is supposedly supposed to be the first ever computer bug. And there's a link to it over here, but it turns out this is actually an old wives' tale that somebody kind of embellished this story a little bit that actually wasn't the first ever computer bug that was actually a bug. It's a little bit made up, but this is going back 50 years. There's I think it's on September 9th, there's a Computer Bug Day, and it's supposed to be celebrating the anniversary of this first ever bug, but a little bit of old wives' tale. So a little bit more seriously, had a problem with spacecraft Mariner 1 that it ended up having to actually get destroyed by the launchers after only a few minutes after its takeoff because they noticed that there was a computer issue inside of the computation of things where they'd actually logically figured out a lot of stuff correctly, but there were some numerical issues that were going on where they noticed that the trajectory was not quite what it was supposed to. So they had to actually have it, they basically caused it to explode themselves because they realized that it was better to do it under a controlled fashion. And it turned out that just the exact communication that they were using they had basically 5 minutes of contact where they had the ability to destroy it, and once it got past that time, it was completely out of their control. They couldn't really do anything about it, so they kind of made this very quick decision that, okay, we should just destroy it right now and not take any chances on it getting worse. This was all caused, though, by some sort of computer bug where the software was just not calculating the angles and the directions that it should be going correctly. It's a little bit of debate on what the actual bug was. A very difficult issue with bugs is that they're often hard to reproduce a bug, and especially when you have something like a spacecraft that you can't exactly run it 5 times, and then if the first 5 times it crashes, and then you fix the bug the 6th time, that's a very expensive bug to try to deal with. So they had a lot of trouble trying to investigate what the reason for this bug in the first place was, but certainly this was a big problem. Other more recent issue is all of the Toyota cars where they had issues where they were accelerating and the anti-lock brake systems were not working the way that they were supposed to. It's kind of almost, you don't think about computers being inside of cars, but there is a computer that's trying to make decisions on things like, is the brake actually getting too tight? Do we need to do different sorts of things? So this ended up costing Toyota quite a ton of money and just very bad publicity as well, having to recall all of these different cars. Actually, the Prius is not a culprit of this, so I kind of framed the Prius a little bit. It's not really fair to do it. It was really a Camry that was more of an issue, but generally they had all these sorts of problems. So I think kind of a good question to ask, why are all these bugs happening? Can't we stop them? Is there some way that we can avoid bugs in the first place? Because programmers are very, very smart people. I mean, why do they actually have all these bugs? Doesn't really make sense. So what can we try to do to minimize this thing that's constantly always occurring? So the way that I try to think about this, something known as Miller's Law. That what Miller's Law is, it's this person named George Miller who observed that at any point in time, we can keep track of about 7 things in our head at the same time. For different people, it might be 5, might be 8, but there's some number around that range that you can keep track of about that many things inside of your head. Now, he used this word chunk, or the word that I'm using is thing. And what chunk means, it's a little bit vague, but it has to do with the size of the data that you're doing. So depending on how big your groupings of data are, you can either store a lot of information in your head at once, or you can store very little information in your head at once, depending on whether you've grouped things into 7 big chunks or 7 really small chunks. So I have a little example just to kind of demonstrate this. So in the following slides, I'm going to show you a couple of different letters. And I'm going to show them to you for only a couple of seconds, and I want you to try to memorize this. So this is basically testing Miller's Law. What we're going to try to do is say, can we keep track of all these letters in our head at the same exact time? So I'm going to show them for a couple of seconds. We're going to see if you can actually memorize this. So, okay, everybody ready for a big experiment? So try to memorize the following slide. So take as much time as you need. Try to memorize this and see if you can keep it in your head at the same time. Anybody need more time? Okay, so I think everybody was fine with this probably. So, okay, let's increase this a little bit. So can you memorize this in your head at the same time? Probably everybody's still fine with that, not really much issue. So, okay, let's start to increase this size a little bit. Remember, he's claiming that you can keep about 7 things in your head at the time. If you try to do more, then you end up having a little bit of trouble. So this one I think most people probably are still actually fine with. You probably can just remember these 5 things all at a time. Okay, now we have a 7 things. And so your goal is to memorize this so that way you can keep it all in your head at a time. But one thing to keep in mind, when you're trying to memorize this, you're not really allowed to take any shortcuts. So you can't try to look at the last 3 letters and notice that there's any kind of pattern. Because if you remember the last 3 letters spell Anna with a slightly weird spelling, then you've actually not memorized 7 things. You really memorized one thing, which was that it was Anna. And so what you did was you memorized maybe NGR, Anna with a weird spelling. That doesn't count as actually memorizing 7 things. And so what you've actually done in this case is you've kind of made a different size chunk, a different size grouping of your data that's a bit smarter and helps you try to memorize all these things. Now, okay, so this one you can do that. If I take this same exact amount of data and I just rearrange the letters in this, I get the word anagram, kind of a little bit of a meta reference there, and everybody can memorize this very, very easily. And so in this case, you have the exact same amount of data on the slide, but there's no problem that you have learning it because it's just one word. You group this in a way that's intelligent. So when you have things grouped in a kind of poor way, you end up not having as much success trying to understand it or learn it as if they're grouped in a very good way. So generally, I think it's very important in these kinds of problems, if you can group everything together, then that means that you're going to be able to understand it better. And what we basically did was we abstracted the idea of individual letters. Because when you memorize anagram, you don't really memorize it's A-N-A-G-R-A-M. What you did is you memorized this one word anagram, and you had a technique that if you needed to get the individual letters, you could figure it out based on that word. But you're not consciously thinking about anagram or each individual letter in anagram at each time. Similarly, if I said write this word on a piece of paper, you're not thinking about the letter A as being 3 different lines that are connected in a particular way. You're just remembering this abstract idea about what the letter A looks like, and you know that if you need to draw the letter A, you know how to do it, but you're not consciously thinking about this as just a sequence of lines. If you thought about this as a sequence of lines, you would not really be able to do this at all. So, okay. What does this really have to do with programming? So why do I bring this up? Well, generally, I think the reason bugs happen is that you understand all the little pieces. So if I show you one line of code, usually you can figure out what that one line of code actually does. It's just one line. Maybe it's a complicated line, but you can still figure out what's going on. But the problem is that a computer program tends to have thousands or even millions in some cases or billions of lines of code. And when they're not combined in a smart way, you end up just having billions of lines of code that are completely jumbled together. And you have no way to really understand what's going on, because if you want to try to, let's say, debug a program, to try to fix a bug, or add some feature to the program, you can't at the same time remember everything about your program. You're just, instead of remembering the word anagram, you're remembering all these individual lines and trying to actually keep track of them in the same place. So a big thing about programming is trying to take your big concept and try to sort of chunk it together in the same way that we took the concept of the word anagram, and instead of viewing it as a bunch of lines, we first grouped all these lines into individual letters, and then we grouped the letters into an individual word. This is the same sort of thing that you want to do when you're programming, that you want to take your big thing and try to sort of group it together. You don't necessarily, when you do this, then need to think about each little individual command. And so this ends up making it a bit easier. So there's a lot of techniques for trying to do this. This is, I think, kind of the main way to avoid bugs in a lot of ways, is to keep your programs as simple as possible. Now, they're still very complicated programs, and so you can't just delete the problem in a sense. But a lot of these different things like methods, functions, classes, variables, all of these things, one of the key reasons that they're created are to try to give you a mechanism to be able to chunk or group all of these things together. And so a lot of the things that we talk about, they're going to be things where it's not necessarily that you have to do it in one way. You could definitely do it in a different way. But a large way to remove bugs, or a key way to remove bugs, is to almost not introduce them in the first place by giving you some sort of structure in your program. So have this notion of one technique of doing this is something called what you could say is hierarchical code. So what this is basically saying is, if let's say you have 1 million tasks that you want to do, rather than just map out your 1 million tasks, you want to try to think, well, I can only keep track of 6 or 7 steps at the same time. So let me try to take these 1 million steps, let me split them up into maybe 7 or 10 or 5, depending on your exact problem. It might differ a little bit, but let me try to split them up into many smaller steps. And so in this way, you can think about your big problem in terms of solving 5 or 6 smaller problems, and then you can take those 5 or 6 smaller problems and do the same sort of trick. At some point, you eventually get to the case where you've split it up so many times that you now have just very, very simple things. Yeah.
I have a question. So if we can have on the 7 chunks in memory, so does there exist a person who knows, for example, understands the idea of the kernel at the time, or maybe there is no such a person who can say, okay, I understand the Linux kernel?
So the way that, good question. So can you understand the entire Linux kernel or the entire computer? You definitely can, but you're not thinking about every little detail at the same time. So the idea is, if you want to understand the kernel completely correctly, what you would do is you would say, let me break it up into the individual components of it. So I don't necessarily understand at the same exact moment every little piece of it, but I understand a kernel is composed of X, Y, Z, A, B, and C. I know that's the general way that they work, and then if I want to think about X, Y, Z, A, B, C, I also understand separately how those work, but I'm not thinking about the individual pieces of each one at the same time. So the idea is to not you sort of have a technique in the same way that for anagram, we don't really consciously think there is a letter with a slanted and then another slant and then a cross going in the middle. We know how to generate that information. If somebody asked us, can you describe the letter A to me? We would be able to do it. But when we think about the word anagram, we just think, this is what its spelling actually is. We don't even really think quite in that much detail. If one then asked, okay, now that you have the spelling, can you tell me even more detail about the individual letters? We could certainly do that by then describing those things. And you could even take this a step further and say, well, how do you describe this line that's going diagonally? And you would say, well, that's actually a bunch of pixels that I drew going up with this particular pattern. And when you do this, you know everything about that word, but you don't know everything about the word at the exact same time. So this is the sort of thing you want to do when you're trying to, not even just programming, but really to understand anything. This is what the technique that you're using.
Can the program be smaller if you split?
Pardon?
Couldn't the program be smaller?
Yes, so this is a good question. So if you split your program up, how will that affect the runtime of your program? So there's a couple of schools of thought on this. So first of all, I think generally splitting your program up into adding extra functions, it's not going to slow down your program too much, because by taking your 1 million things and dividing it into 10 smaller problems, you still have the same number of steps that you're doing. You've just kind of moved things around in your code a little bit. So for starters, it generally won't slow it down too much. It will have a little bit of more overhead that you're dealing with. I think there for sure is a little bit of a trade-off that you'll want to do. One big feature about having your code split nicely is that if you do this in the first place and then you realize that actually this is too slow. It turns out that this idea of splitting things up, it is actually making it a little bit slower. I did all these things to try to do it. Now, because it's split, it's going to make your code a lot easier to try to actually pin down exactly what part of it is slow. And then you can take that one little piece where this is causing a problem. And so generally the approach that I use is code it in the kind of cleanest, most natural way possible as far as what the code would look like. Almost never will the actual splitting of problems be the cause of your runtime. Usually there's some other bug that's causing some runtime issue, or you haven't properly maybe chosen the right data structure that we'll talk about in a little bit, and that somehow caused your issue. Very infrequent that it's caused because you just have too many function calls. The computer can jump to a function very, very quickly. In the highly unusual case that this is actually the problem, maybe you had some extra variables that you were passing to too many different functions and somehow that was causing an issue. Because you've now split it, it's a lot easier to go from the split problem and kind of combine things a bit more together than it is to start out with your program that's a bit of a mess and then try to split it up later on. So generally, I think runtime is important, but it's better to focus on trying to remove bugs, because if your program works fast but gives you the wrong result, that's probably worse than if it just doesn't if it doesn't complete in quite a good time. So, okay, so this is kind of split. Actually, yeah, I mentioned this on the very bottom here. It says code is more reusable. I think that that's a key aspect also about splitting your problems up. So then when you do this sort of thing, if you've actually split your problem into a lot of smaller pieces, you now have individual problems that you've solved. And so this means that you can more often take the code that you used on one day and actually use it for another project instead of trying to start from scratch. So one metaphor people will use when they think about programming is that you could think of a program like a house that's made out of bricks. And what you would like to do is make your bricks as small as possible, so that way if your program changes a little bit, you can just swap one brick for another. On the other hand, if your program's not made out of bricks and it's just this one huge concrete slab, if you want to make some sort of change to your house and somehow maybe add some feature, you really need to swap the whole concrete slab. And that's very difficult to try to do. So want to try to make a program out of as many small things as possible. So this is also just an example about if you wanted to try to think about kind of hierarchical code or just reducing the amount of things that you have to do. This is a case also where a bug could very easily get created. A very good way to make bugs is by copying and pasting code from one place to another. It's kind of almost guaranteed to make a bug. And every time you say, this is the last time I copy paste because you found your bug, you're still going to do it anyway. But so this example is that you have this one particular problem that you want to do 500 different times. And so you just copied and pasted this one particular way to do it because you were doing it that many times. Now, when you realize that your question is changed a little bit because you want to say, well, let me now add the functionality to be able to support something in the French language. Well, now you're going to have to change every single one of these lines because you've made this sort of update in this many places. And this is almost certainly going to cause a bug as well, because you're going to forget that in one case you needed to change something that you forgot to change, or you'll change something accidentally that you really shouldn't have changed, and so you end up running into issue. On the other hand, if you've kind of designed your program with very, very small pieces in it, then when they tell you, oh, now we want your program to work in both English and French, well, because you've split your program very smallly, you're just trying to insert this one extra brick somewhere. And so although it's not necessarily trivial, you still could cause bugs in the process. You're a lot more isolated from the rest of your program. And so the sorts of mistakes you make are a bit more contained to one region. So we'll look at some of the things you could do to try to minimize this and try to avoid these sorts of things to make your code a lot more reusable in these sorts of cases. So one example of also hierarchical, not code now, but hierarchical data, if I think about classes, this is the main purpose of classes, that you could, if you wanted, you could make your program never use a class, and you could have 25 billion variables that you wanted to use in your program. However, if you do this, you're now going to be causing an issue with Miller's Law, because in order to write your program well, you have 25 million variables. You don't know which one to actually use. You're trying to remember the variable x is something, the variable y is something else, and you have your names are x1, x2, x3, kind of terrible names. Arrays are a solution partially to this, because what an array is it's a container that holds many different values of the same type. And so that helps you give some structure to your data, in that instead of thinking about your 100 different elements that represent some particular set of values, you can now think about just one array, and you know from that one array, you know how to find the individual elements. Very good way to do it with arrays, but they have a limitation that they all have to be the exact same type. So you can't make an array that's partly integers and partly strings. That kind of thing just wouldn't work. Classes are kind of a generalization of an array in some ways, in that they allow you to, instead of just working only with numbered values of the same type, you can now give names to some different values and still group them into the same type. So this kind of brings it to the idea of data structures. Very often what you try to do in terms of using classes is you could have some simple types. So you might have a type like a char that takes up 1 byte, or a float, or maybe even a pointer that takes up 4 bytes. These are kind of your most basic types, and what you try to do when you're programming, this often helps to reduce bugs, although as pointed out, it does in some cases make your program a little bit slower, but I would say that almost for sure the amount of slowness in 99% of cases is going to be outweighed by the fact that you can focus on fixing this and not waste your time on fixing bugs. So you start out with these basic types, and then you can make composite types that are based off of both basic types and other composite types. So what I might do is I might say, let me take my few simple things and try to group them together into one class or one struct, and this would try to mix these things together. And then I could take that new type that I made and even group that into something else further. So this might be what it looks like in memory, that I have some sort of, here's just my char, my float, and my pointer, and then I might group some of them together into one particular structure instead of having this, and also this thing sort of over here. This is grouping one of each of those three together at the point. So it's kind of a little bit like these dolls, where you would have something where you have an object that's inside another object that's inside another object, or so you have maybe this is your very simple data type, and then you have this other one that's composed of some other data, and then you keep on sort of building up, and then you always can deconstruct them in this sort of way. And you sort of know when you're at this bigger one that, okay, it's consisting of a whole bunch of other things, but you're not consciously thinking about exactly what's inside later on. In fact, the only thing that's really visible to this particular doll is the one that's immediately to the right of it, because normally these go right inside of each other, so you can't see all the way down to the base. So I think, kind of summary about this, if you're using data structures and classes, the main point of this is not necessarily giving you more functionality, but they're largely just a technique for trying to reduce bugs, because you're able to group your data. And so what grouping your data allows you to do is only think about a few things at the same time. When you think about only a few things at the same time, you can really understand everything about that data at the same time. If I gave you a sequence of 45 letters and you said memorize these 45 letters, almost for sure you would make a mistake when you transcribed it to your paper. On the other hand, if I told you just some sentence that was a very famous sentence, and then I said transcribe it to your paper, even if that sentence had 45 letters, so to be or not to be, that's the question, most of you will transcribe that correctly and not make any mistakes because you've organized things in a way that you don't need to memorize every letter at the same time, and so you won't make this sort of mistake. I think coding is exactly the same way, that if you try to group everything wisely, then you don't need to think about each thing in tiny little detail at the same time, you won't make a mistake. On the other hand, if you don't group it wisely, then you're almost certainly, I mean, it's kind of hard to describe exactly why, because, I mean, why would you just make a mistake if I put 45 letters on the board and then said write them all down on a piece of paper? It's hard to explain because nothing in that was really hard. You understood what you had to do, but you still made a mistake anyway. And that kind of thing is what will happen with coding most typically. So, okay, this was kind of a topic about how to reduce your bugs. I see I didn't give you really any suggestions on that yet, but that's some of the things that we'll talk about in some of these lectures. Another key topic is pointers and memory management. So this comes up mainly in C++ and C. So this would be a key topic there. That kind of, I think, good question to ask about them is what the, no pun intended, but what the point of pointers actually is, because why do we even care about learning them in the first place? So wanted to give a little bit of a high-level example of why a pointer would actually be useful. Couple reasons. They let you store more data in memory. They actually will sometimes save memory. And then there's also this topic of polymorphism, which is a little bit more advanced. Might not come up so much in programming that you would be doing, but it's something that in some cases you might want to use. So this is an example of a function call. I think it's good to kind of remember what the rules of functions in both C and C++ are. So we have our main function, and in our main function we declare a variable y, we give it the value of 3. Then I call the function foo, and I pass to it as input, I write y. Now you want to remember what actually happens when you do this. So when I call a function, I'm not passing a variable called y to my function. What I'm actually doing is the computer is going to look at what you've written between the parentheses that follow the word foo, and it's going to evaluate what you've written here. So it's going to figure out what is the value that's over there. And in this case, the expression that's here is the variable y, which has the value of 3. And so this code is going to be exactly the same as if I wrote foo of y or foo of 3. It doesn't matter where the value came from. What matters is that that thing has the value of 3. So the computer is going to jump to this function foo, and this says that when you call the function foo, there's going to immediately be a variable called x that has its value coming from a different function. And so what I'm doing then is I'm going to create a new variable called x with the value 3 in memory. So, okay, what would this look like kind of in a picture? We have y has the value 3. We then call our function, and then x has the value 3. Important thing is that there's 2 different places in memory, each with the value of 3. And so this works fine. There's no problem with this, but key thing just to keep in mind, if you changed x inside your function foo, it wouldn't change y in your function main because they're different places in memory. So if I wrote here x plus plus, no impact on y. So, okay, this works fine. Variable x gets erased after my function ends up finishing. What if I had a slightly different problem though? So instead of y just being an int, let's say that I had y was this really big array of size, I guess 10 or 100 million or whatever size that actually is. So what's going to happen when I call this function? Well, the exact same procedure would end up happening where I would create my array. My array is going to take up 1 billion bytes in memory, or maybe 4 billion bytes in memory, depending on how big an int was. And then I'm going to jump to my function foo, and I'm going to replicate all of that memory into this variable x, and then I'm going to execute stuff, and that variable is going to get erased, and this is a huge waste of memory. It's something that, first of all, you might actually have issues on your computer that taking this amount and duplicating it twice, that kind of thing might cause a problem where, depending on your computer's limitations, it might just crash your program because you're using up twice as much memory in your program as you otherwise would be. Even if it doesn't cause it to crash, it's going to be very, very slow because you've now told the computer when you call this function that instead of just jumping to the function and giving one value to the variable x, you would have to actually copy every single value in this array to this other function x. And so this sort of thing is actually going to be very slow in that case. And so if you're not kind of careful, this is where you could run into a case where by splitting your problem up now you've caused some other issues with memory. Now, where does a pointer solve this problem? Well, sort of a little bit of analogy to work with. So let's say that you had several different contact lists. So you had a list of all your friends, you had a list of your family, you had a list of acquaintances. So these are like Google circles or something. Now, there's some overlap between these different things. So some of the things that appear in one list will appear in another list as well. Now, for every single person, you want to store lots of contact information about that person. So you want to store things like phone, address, email, name, and let's say that this amount of data takes up very large space. It takes up 100 megabytes inside of memory. So what would be a way to store this data that would require the least amount of space that would be possible? So this is kind of just what it might look like. The key thing is that you have some overlap between the set of people that are your colleagues and the set of people that are your friends. If you didn't have this overlap, you wouldn't be saving any memory doing it one way or another. So what would be a good way to store this? Any ideas? Not in terms of the code or anything, but just at if you're doing this on some pieces of paper, you wanted to actually put all this information, how would you go about doing this to try to reduce the amount of writing or whatever that you've done?
You have all the information stored, and then you have lists that point to different entries in that information.
Yeah, exactly. So what you would want to do is you would want to put on, let's say, one piece of paper, information about a person. And then on so each person will get his or her own piece of paper to describe all the information. And then you'd also maybe give each piece of paper an ID or a number. And so you have 100 pieces of paper, one for each person. You give them numbers from 1 until 100. And then for each one of these lists, so your list of colleagues, you would just write your 20 numbers, or however many colleagues you had. And then for your list of friends, you would write your 12 friends. Instead of having to write the entire information about that person, you would just write the particular ID that they had. And so this would save you a lot of writing, because you have your one person that's part of 20 lists, and instead of having to duplicate the information for that one person 20 times, you would now just write that one ID, which is just one number, 20 times, and then one time write the information that's associated with that ID. And so this is effectively what a pointer actually is saving you. So it's kind of useful to do this. So this is the idea. Make a numbered list of all of your contacts. So number all your contacts from 1 until whatever number. And in one particular list, include all the information about your contacts. So this is basically your stack of papers of all the different people that you have. And so you have one piece of information for each person. So you have the ID and all of the different things like their name and their email. And then you make one list for each of your contact lists. And so because the list only needs to maintain the numbers now, this is where you're going to save a lot of memory. One other nice benefit, let's say the contact tries to change some of their information, so you need to update the phone number for a particular contact. Well, now instead of needing to go into every single list, it's actually a lot easier to make this sort of update, because you don't actually, let's say I change my phone number, it doesn't really make sense for you to change one of your lists of family. That's kind of a strange thing to change. So also, I guess I'm not related to you, so that's also another reason. But if I wanted to update my phone number, I should just update information about me. I shouldn't really be going into each separate list that contains me. And so that's kind of a nice thing as well, that you can change one place and then it would end up impacting all these other things. So with a pointer, in terms of this analogy, it's almost the same thing. That what you're doing is you're not storing the data in your variable, you're storing where to find the data. So in the analogy, our list stored what ID should we actually get. That ID was then used to get the information that we needed. So a pointer is going to store the address of something, and then we use that address to try to get the information that we needed. So this is something that in a lot of cases could save you a lot of memory, which would end up improving runtime of things, because instead of actually storing this data 100 times, now you just have to store where to find the data 100 times, which is quite a lot less than the actual data itself. Also, kind of a little bit of tangent, but this also goes to sort of how you would design a database to try to think about some of these things, because a database is just a table of all these mappings. So you might say, well, how do I represent all of these different contact lists inside of a database? Actually, it would be very similar to this sort of idea, where you could, if you wanted, make each contact list, you could have this be some sort of entry where you maintained all the information about each different person inside that particular row. Normally what people tried to do, though, is they tried to have maybe one table that lists all of your people and then another table that's actually all of the lists, which is somehow connected to those things. This is a little bit of tangent, though, because it's not really related to pointers. It just kind of comes up here. Now, so that's the benefit out of using pointer. It saves you a lot of memory. It lets you do things like pass things from one function to another without making you duplicate all of that data. Problem is that they're really kind of annoying to work with. So you start looking at the syntax of them in C or C++, and they're really a mess. And then there's this whole other thing in C++ that I haven't even mentioned, which is that in C++, they have pointers. They also have something called references, which are not the same thing. And if you've ever worked in Java, confusingly, a reference in Java is actually the same thing as a pointer in C. And so, like, why did they bother making this messy? So that was kind of a bad idea that they made it that messy, but they did, and there's not much one can do to change it. But so these are examples of things you do with pointers. So I declare a pointer x, and I know I'm declaring it because I have a star over here in my declaration, and then I use this ampersand operator to try to get an address of y. And so I can do other weird things where I have double stars and I'm dereferencing them. All these things are perfectly valid. You want to try to avoid doing this when you can, because it's the sort of thing that would cause a bug maybe, because you're now, when you're writing this line, you're thinking about 7 things at the same time, but you will have to do these sorts of things in some cases. And so it takes some time to try to figure out how to actually use these correctly. Other problem with pointers have these issues called memory leaks in C or C++, where one of the benefits of pointers is that they give you the ability to control memory a bit better. So you're able to, when you're working with pointers, for example, you can use the same spot of memory in more than one function. And that's very useful in a lot of cases, because especially this case that I'm describing where you want to call a function and you don't want to copy the data from one place to another, and so both these functions share the same exact data. Problem is that because you're now given this control, you have to use this control correctly. And if you don't use this control correctly, you end up running into several different issues. There's some that will crash your program, where you did something, it no longer works, you now have some sort of segmentation fault, and it causes your program to crash. In other cases, you end up having sort of the opposite problem, where your program still works, but then after it runs for 3 hours, then it ends up crashing. Third issue that can happen is kind of maybe even worse issue, which is that you run your program, and sometimes when you run it, it works correctly, and sometimes it doesn't. Almost for sure, if you had this sort of thing, there's some sort of memory issue that you ran into where you just weren't properly using it. So kind of common thing that people run into, if you've ever left your web browser like Firefox or Chrome open for way too long, this is what will end up happening to it, where you have what's called a memory leak, where there was some issue where they gave the programmer the ability to release some memory, and they just didn't. And it's not that big of a deal in some ways, because they only wasted 1 byte every, let's say, second. But it turns out that then when you leave your browser open for 2 weeks, then at some point all these bytes end up running out. And so the computer runs out of memory. That causes it to crash. When you restart either the browser or the computer in some extremer cases, everything's fine. All the memory gets released at that point. But that's what ends up causing the thing to end up crashing. So if you don't do this correctly, that's where you end up having problems. And it's really difficult to find, because how, as a developer of Firefox, are you going to avoid all these memory leaks once they exist? Because you could just leave your browser open for 2 weeks and then you notice it crashes, so you discover you have a memory leak, and then you remove one of these memory leaks or one of these bugs, and then you're going to re-wait 2 weeks all over again just to try to determine whether you've gotten rid of them all or not. It's not very practical to do. You'd spend your whole life basically chasing down these different things. So very kind of troublesome aspect of pointers in C and C++ is that you have to make sure you're properly deleting all of your memory, otherwise you end up with these sorts of things. Maybe it doesn't come up that often because you're not designing a web browser, so maybe it's not quite as the particular issue of leaving something open for that long, but certainly you would have other cases where you were somehow not properly, you were maybe trying to use memory that you had already gotten rid of, and so then you would have your program crash. So, okay, kind of a little bit aside, so definitely I think spend a lot of time on pointers. This one would actually probably almost be maybe 2 talks, because I think there's a lot of stuff that you can do wrong with pointers, a lot of stuff you can do right with them. So I think that one is worthy of a bit more discussion too. Another potential topic, standard library and sort of what to do with it and what the STL is, how this works inside of C++. be nice if this was kind of really just super easy to use, but I think it takes a little bit of getting used to how to actually work with these things. So just a little bit of background of what it actually is. So there are a lot of library functions and library classes that come with C++. So if you're working in C++, you have a bunch of code that is given to you that comes with the standard installation of C++, and it's called the STL library. And you can use these functions as part of your programs. They're written in C++, so they're not really built into C++ per se, in that they're kind of extensions of C++. They're just so that when they develop C++, they realize here's a bunch of common problems that we would like to have some common technique that people can use. So then rather than every different programmer having to start their own thing from scratch, they can use these libraries. So main benefit of using them is that you don't have to write the code yourself. That kind of saves you a ton of time. But you have to kind of, I put it in quotes here, learn them out. You have to sort of figure out how to actually use these. And I think a language like Java, it's actually pretty intuitive to try to use. In C++, it's somewhat intuitive, but it takes a little bit more getting used to how you'll actually use them to get them done correctly. There are some kind of weird things that even when you use the library, if you don't use it correctly, you still can have your program end up crashing with different sorts of segmentation faults and other weird things. So an example of a library object. So we know about arrays, hopefully. So an array is a built-in structure in C++ that lets you store multiple values of the same type. It's not a library object, it's just built into the language itself. So if I want to store 100 values, I could create an array, put 100 values, if they're all the same type, into that array. Not a library object because it's built into the language. Now, so what are some downsides of arrays? What are bad about arrays?
You don't know the size of them.
Yeah, so they don't keep track of their own size. So you have to keep an extra variable that will somehow manage what its size is, so that way you know how big it is and you don't have an array out of bounds problem. What else is bad about that?
Same type of data, right?
Same type of data. That's not actually stored by that's not actually solved by the STL problem. So it is the same type of data. What's a limitation that you have with an array? It's a fixed size. So not only does the size have to be stored, you can't change its size unless you want to really do some kind of advanced stuff in terms of what you're dealing with pointers. But even in that case, you're not really changing its size, you're kind of just manipulating it a bit. So there's an object in C++, something called a vector, that you can use to deal with this particular problem. So you can use it when you want to store multiple values of the same type, but it solves this sizability or resizability aspect. It also solves the array variable now keeping track of its own size. So the way that you would do this is sort of the equivalent with a standard array and with a vector. In this case, we create an int array of size 2, put into it the elements 3 and 2. In the case of a vector, we now use this function called pushback, that what that does is it adds an element to the very end of your vector. Notice that when I create this vector, I don't actually give it any sort of size, I just create it. That's because a vector is resizable in this way. It's something called a dynamic array, meaning it can change its size. Now, this is convenient for a lot of these cases. There's also a way, in the same way I called this function pushback, to try to add an element to my vector. There's another function that gives me the size of a vector. So I don't need to constantly have two different variables that are keeping track of the size as well as the data. So this helps with things like Miller's law, because you only have one variable. In this case, you always need to remember two things, the array and also the size. In this case, you just remember y, so just the vector. You know that if you need to get the size, you can get it by calling a function that gives you the size, but you're not consciously always thinking about that at every single point in time. So this is great, but it turns out it takes some practice to try to figure out sort of how do you read over the documentation to learn this is what the pushback function actually does. This is how it actually will work. So a kind of useful application of this. So here's a particular problem that says write a function, given an array of int, return all of the positive ints in that particular function, or in that particular array. So if I had a regular array, what I would do to solve this problem is I'd create a new array, maybe, that would store, the idea of this new array is it's going to store all of the positive values of my original array. And I'd set up some sort of for loop or while loop to look at my original array, check whether or not the element is positive, If it's positive, add it to my new array. If it's negative, then I don't add it. But the problem, as it says at the bottom here, is that you don't know how big this array should be when you first create it. So you have kind of a couple of different options that you could do to solve this problem. So the first one is you would say, maybe what I'll do is I will first create an array that is bigger than I could possibly need. So maybe what I would do is I would create an array that had the same size as my original array. And then I would store all of the things in my first array that were positive in this new array. And then instead of just returning the new array, I would somehow also keep track of how big this other array actually was. But this is kind of, so I'd have my big array and I'd say the only thing I care about in my array is the first 20 elements in it. Everything after that can be ignored. Bad thing about this is now you're increasing the chances of you having a bug, because you now have this case where you have an array that has a size of 100, but because there are only 20 elements in it, you've only filled in 20 things, and so you now have to remember, oh yeah, the second half of this array, it's kind of garbage values. It's not anything I want to do. If you forget to do that correctly, you somehow make some sort of mistake, now you have a bug that maybe is a little hard to deal with.
Could guard against that by initializing the array for positive values to negative values.
Right. So this would be a good idea to start. So you could do something to try to help that a little bit. You could make your new array that had, since you sort of analyze the problem and you say, well, I'm only moving the positive values into my new array. So why don't I initialize my new array to be all -1, and then I can move all the positive values, and now at least I only have to give back one information in some ways, but I still am kind of giving two pieces of information, because I still have to remember my array, this is what I'm looking for, and then I also need to remember only look at values in the array that are greater than 0. So that would help in some cases a bit.
You've adapted it to the problem, which means
right.
You can't use it for any other
Right,
purpose.
and so that's the other thing. So now it would be easy for somebody then, I mean, you look at your function, you say, oh, I wrote this great function called find positive elements, and then you forget, oh yeah, that's right, I had this one nuance that when you call this function find positive elements, this would be how you would deal with it. So, I mean, that solution will work, but I think this is where something like the Miller's Law and sort of trying to keep track of lots of things, if you do this kind of thing once in a while, it's okay. If you do this sort of thing too many times, then you're bound to forget at one point that, oh yeah, when I call this function, I need to satisfy this other thing. And then you'll spend several hours trying to debug your problem, and then you'll remember, oh yeah, that was the problem, that's why I had this assumption, this was what the issue was, but you will have wasted several hours in the process of trying to do this. So other idea that one could do, which is a little bit better idea, is you could, instead of making a new array that was bigger, you could have two loops in your function here. So you could, in the first loop, just count how many positive values you have. And so I would go through my original array, count how many I had. This would then determine how big my array should be. And then after I've determined how big it should be, then I could set up a second loop that would actually go in and insert things into this new array. So this is a good idea, and it would work completely correctly, but now you've also doubled the amount of code that you had. So if you doubled the amount of code that you wrote, you're increasing in a lot of ways your chance of a bug as well, because you have more code and more chances to try to make a mistake. So this kind of thing would work, that would give you the right result, but you'd have to be very careful to make sure that you did it correctly. There's also kind of a little bit of messiness involved in that when you're copying from one array into another, you actually have two indices to keep track of, because you have an index from your source array, and then you have to keep track of where in your destination array you want to move it to. Now you've added a couple of variables. This is also increasing the chance that you have a bug. On the other hand, if you did this with vector, you wouldn't actually have to think about any of this stuff, because the vector, it has no size, in terms of no fixed size anyway, and you just say push back, it actually keeps track of where the end of the vector or the end of the array actually is. And so you would just set up your loop to go through your array. You would create a vector before your loop, and then you'd call pushback in some cases, and in other cases you do nothing. And so in this way, you reduced the amount of code you wrote because you didn't need to write two loops. You reduced the chance of error because you didn't have all these null values at the end. You also reduced the chance, or negative values at the end, meaningless values, depending on how you sort it. You also reduce the chance of error because you didn't have to keep track of where in this vector you would put things. And so this sort of thing ends up saving you a lot of grief in some cases. Obviously, it's a little bit of a small example in that I think probably in this case, maybe you could do it anyway, but I think that when you start getting more complicated problems, this is where it's important to try to use these STL things like that. So main benefit of using vector class, it solves this particular problem because it lets you resize an array. Because it keeps track of its own size, you also have fewer variables that you need to pass around. So I could return a vector, and I don't need to return the vector and the size because the vector is actually able to keep track of its own size. I can write actually foo.size if foo is a vector, and in this case it would print 1 because that's actually just the amount of elements that I've added to it. So this helps reduce code. Now there's a lot of different standard library objects that you can use. Vector, which is meant to represent an array. List, which is meant to represent a linked list. Something called a hash set, a map, some other things. And there's kind of a tough question about how do you want to choose which one of these things will work. Because a lot of these actually are all for similar problems. In that if you think about these different types, if you read a little bit about them, they're all meant to try to store data that all has the same type. And they just do it in a different technique. So a list, since that's a linked list, that's something where it's using a technique where instead of storing one big block of all your data, it actually stores one thing at a time, and each thing then knows how to find the next block. And now it's kind of the same sort of approach in that you think of it now as kind of a chain of different things. So if I was storing all my data, instead of just having one long list of it, I now have each element has actually two things in it. It has the data itself and also where to find it. And why would you want to use list over vector? Or why would you want to use vector over list? There's something called a hash set that you could use. Again, it stores somewhat the same thing. It uses a different technique for trying to store it. How do you try to choose which thing is actually best? Well, this is where actually the runtime of your program would greatly be impacted because there's different things like if you think about the way you'd store a vector. So a vector is actually stored as an array. So you see it as this convenient thing where you can use pushback and try to just add things and resize it at the same time and do these neat things. But it's still an array in terms of that they've basically hidden from you the fact that they're using an array. So what this means is if you had a lot of things where you wanted to, let's say, let's say you wanted to add a bunch of different elements to your array. At some point, your vector is going to run out of space because the code for vector is using an array to store all these different values. And when you keep adding to it, eventually the array that it's using will have no more space. So what the vector code does is it says in this case, all right, well, you ran out of space, but vector is resizable. And so what we'll do is we'll have some code that will make it appear like the vector resized things, and it will copy things into a new array and kind of just make it bigger so that it has more space. But this is going to be a little bit slow to try to do. So it's not going to happen that often, but it is a little slow in that in some cases trying to add things might not be that fast. It's also not that fast to try to search for a particular element inside of a vector because if you have an array and you're trying to search for an element, you have to look at every single element in your array unless it was already sorted or you had some sort of technique that you could use to try to take advantage of it. On the other hand, there's another data structure, maybe something called a binary search tree, where they store things in a smarter fashion that allows you to, instead of just always having this exact look at the first element of the array, then look at the second element, then look at the third element, you can store it in a technique that lets you search for elements in a faster approach. And so some of these different structures, they're better maybe for searching, others of them are better for adding, others of them are better for deleting things. This is where knowing a bit about the data structures that these are actually using, that ends up coming in handy quite a bit to try to improve your runtime. And that would actually have a big difference because if you have things where you're searching through a million pieces of data and you're able to do that instantly, that's going to be a lot faster than if you have to look at every single one at a time. So we can talk some about the different data structures that are there and what some of the reasons you might use one, why you would want to use vector in one case, why you'd want to use list, what the advantages are. In terms of the code that you write, they're almost all going to be the same. And that's what's a little bit challenging where I say you have to learn the map of how to use them because you could substitute code where you'd written it all in terms of vector and then just replace the word vector with list. and your code would in many cases still compile, it would still logically do exactly the same thing, and all of a sudden now you've turned the runtime from 10 seconds to 4 hours. And in other cases you might have the opposite scenario where you wanted to actually replace vector with list. And so this sort of thing, knowing a bit about how the data structure itself works and what it's good at and what it's not, that helps you in choosing these sorts of things. So a lot of things that you'd want to think about when you're trying to choose which object to use. So it's kind of what functionality do you want? I think you look at what you're trying to solve. Do I want to do this with a vector? Is that what vector is good at? Is that what vector is not so good at? It's also issues of space and memory. So some of these structures maybe take up more space than others. And so again, knowing a bit about how those are implemented and not just kind of blindly just using them without thinking is important. And this third one is important too. So the ease of coding. That also is a factor, because if your code is easy to write, then you can focus more on improving the memory. Whereas on the other hand, if your code is just difficult to use one of these, and you found that for this particular thing I had to write 20 times more code because this thing didn't have this particular function, well, that might be a reason that even if it's a little slower, you say, I'm going to try to simplify my code a bit, reduce the bugs, and then focus on that. So kind of a lot of things. We can talk about some of the benefits of what things are. A couple other miscellaneous things that people had said as far as things that we could talk about. So code safety and security. So I don't think this comes up so much in terms of like the programming maybe that you're doing for physics experiments, but it's kind of a neat topic. So what do you do to avoid your code actually getting hacked? Let's say I have a website that I'm managing an experiment. There are some things that if you're not careful, you could actually maybe somehow run into a problem where you let somebody delete your whole database. And you don't want to have that happen because now all your experiments, you have now erased all this stuff. So what one can do to try to make sure this sort of thing doesn't happen. Anytime that you're interacting with some users, you have to have a little bit of thought that maybe they're going to be kind of a devious user and try to construct things in sort of weird way. Common thing that people might do in some cases is an example of what's called a SQL database injection. That what that means is that you basically ask the user, enter some text, and what your goal is that you're going to execute whatever you're going to basically take what they typed and use that as part of your command. So one command you can use in a database is you can say something like, select all the elements where the name is something. And so what you might do is you might write your web form where you might say, enter your name, and then what you did was you took the block of text that they typed and you treated that like a string, and then you substituted it into your database command so that, let's say they type Dan, then your database command would be select all the elements where the name is Dan. Or alternatively, they type some other name, you said select all the elements where the name is something else. Now, a particular devious user, though, might decide that they were going to type as their name, that their name was Dan, semicolon, delete all the elements in the database. And then what will happen is because you took this particular text that they typed and you just said, okay, well, I'm going to paste this into the command that I'm trying to write. So I'm going to always say select all the elements which, and then whatever command they had. And so then they say, okay, select all the elements which have the name Dan. Okay, they're chosen. Delete all the things inside of the database. Or the other thing that kind of related one that people often do is they'll say Dan or 1 equals 1. And so that's supposedly my name. And so in that case, they would say something, let's say it was remove a user in that case. So they might, I'm trying to delete my account. They say, what's the username you'd like to delete? So normally I'm supposed to type my name, and then it would say delete all the users whose name is Dan. But then they actually said delete all the users whose name is Dan or 1 equals 1. And since 1 is equal to 1, then that's going to actually delete every single user. So this sort of thing, I mean, it's kind of unlikely that you would publish something like this as an experiment and then some student is going to decide to do that, but it's kind of interesting to do it, I think, just as a general topic. Simple database design, so what can you do in terms of the database that you're actually using? How would you manage this kind of thing effectively? Kind of a more advanced topic, but just when you're designing a big program, you have lots of classes, how do you sort of lay these things out? Things like inheritance and polymorphism, what the purpose of them actually is, how you can use them to try to simplify code a little bit in some ways or try to manage things. So these are some of the things that we can talk about. So we have sort of at the very end, just there's a couple things. So there's a little bit of a quiz. So here we have kind of a big mix of things. Everybody knows, so that's good. So if we say that a char pointer, because it's storing an address, it's storing a number, so that means it's taking up the same amount of space as an int, then the second swap is taking up the space of 2 integers and a char, because it's storing 2 pieces of memory that are ints and 1 that is a character. The first one is actually just taking up 3 chars in memory, because there's char A, char B, and then this other char TMP. And so number 1, even though it's not working with pointers, is actually going to end up taking up a little bit less memory. So the way to interpret this, you have an array of char. So when you say ampersand of Schrodinger's cat at 0, in terms of the types, what you have is a pointer to a char, because Schrodinger's cat at position 0 is A, which is a character. So when I say ampersand of that, the type I have is a char pointer. And so when you use cout, and this has to do with library object of cout on exactly how that works, but when you use cout and you're dealing with a char pointer, what it's going to do is print that text until it encounters, so it'll just go sequentially through the text at that address until it encounters this /0 that's over there. And so the first statement is going to print alive until /0. And then the second thing, it says starting from index 6, which is where the letter D is. But the problem in this case is that there's no end. And so it's going to print DEAD, but then it will just keep on going until it reaches, at some point, because accidentally in memory, there was the same value that this 0 value had, then it would actually stop. And so first of all, it's okay to store, this is what polymorphism is, that I have a variable that is an A pointer, but in reality it's storing the address of a B. The reason that you would want to do this in some cases is that you might have a lot of classes that are very common to each other. So an example commonly used is, let's say I had a bunch of classes like square, rectangle, circle, bunch of different shapes. They all will have a getArea function because they all have a way to calculate an area, but it's done completely differently. And so what you might want to do is you might want to make an array of shape. And this is more convenient to work with than having an array of rectangle, an array of square, an array of circle, because you can have everything in just one piece. So you set up something like this where every single one of your different classes that are derived have these different calculate area functions. Okay, so hopefully, I think this is the last quiz question, but hopefully it kind of gives you a little sense of if, sort of what sorts of topics that we would end up talking about. There's just a little slide as far as these are the different people that were helped put everything together here. So I think if you have any questions, talk to me after the talk. There's also, I think, an online forum where you can kind of give a little bit of feedback as far as what topics you would like to focus on, what topics you would maybe think you already know. And so, okay, I think that's it.
So please register for the survey. And just 1 second. So as we are all GAPS members, so Grace and both of you would like to thank you.
Oh.
So we have some small funds, and of course we would like to thank you for the talk.